Okay, and so we're going to pick up with part 4, which says now taking sigma and tau as in part 3, we just reverse the order of the product. So we compute tau sigma now rather than computing sigma tau.
Yeah, so I'll start like we did before and just get them up there because that was helpful to me. And then I guess it's 1, 2, 3.
And 4, 6.
4, 6. Thank you. Okay. Shall we start with 1 again?
Let's start with 1.
Great.
Okay, so 4, 6 does nothing.
Yep.
1, 2, 3 takes 1 to 2.
Yes.
So now I'm carrying 2 with me when I look at what this permutation does. And so 2 goes to 3.
Okay.
So 1 went to 3.
Hold on, I just need to wrap my head around that for a moment. So 1 goes nowhere, goes to 2, and then we're not done. 2 goes to 3. Okay,
Great.
I'm with you now. Okay, great.
Okay, and so then we look at the next step. So we're going to look at where 3 goes, which is nowhere. Then 3 goes to 1, and then there's no 1 here. So 3 goes to 1, so I close.
Yeah.
Okay. Yeah, okay.
Okay.
That happened earlier.
It did. I don't really know why it happened, but okay. Yeah.
Okay, so maybe we look at where 2 goes.
Sure.
Okay, so 2 goes nowhere. 2 goes to 3, and then 3 goes to 4. Oops.
Okay. Now 4 goes to 6. Nowhere. 6 goes to 2.
Okay.
Wait. Oh, okay. I keep getting confused because 6 doesn't show up there, but we used 6.
Right, that's right.
Okay, so 4 goes to 6, 6 goes to 2, so 4 goes to 2 in total. Okay.
Great. Okay, so we've mapped 1 to 3, 2 to 4, so now we have to look at where 5 goes.
Yes. Doesn't move. 5 goes to 6.
Cool.
6 goes to 4. 4 goes to 4. 4 goes to 5.
Okay. And I mean, that's sort of what happened before, is 7 didn't appear, and each of the other numbers permuted among each other. They were cycles, 2 cycles.
2 cycles.
Okay, but the numbers are different. So here
Yeah.
1 mapped to 3, and here 1 mapped to 2. So these aren't the same cycle. So
yeah, right.
So
it's also not just like what happened in part 2, where we like the cycles look different, but they were the same cycle because it was just like wrapped around.
Oh yeah, that's something we have to think about. I forgot about that. Yeah, but 1 is going to 3. Like they're not the same number, even though they don't look different, but they also don't do the same thing.
Right. Yeah.
Okay.
Okay.
So S7 can't possibly be abelian because sigma tau and tau sigma are not the same. Okay, but what if they had been? What if we had?
Yeah.
What if sigma tau had been tau sigma? Is that enough to say that S7 is abelian?
Well, abelian means that any 2 elements commute.
Oh, so if we have a pair of elements that commute, that doesn't tell us that all elements commute.
Right.
So that wouldn't tell us that S7 is abelian.
Yeah.
Are there any elements in S7 that commute? Well, okay, so not doing anything commutes with everything.
Yes.
Oh, but we saw earlier, right? We said that if we had like 1, 2, 3, and then 4, 5, that it didn't matter what order we did that, like this would be the same.
Oh.
Because here, 1, 2, 3 are unchanged, and here 4 and 5 are unchanged, so it doesn't matter which one we do first.
Right. Oh, that's interesting.
And these are disjoint, right? That's That's the name for that.
Yeah.
So disjoint cycles
Commute.
commute.
Okay.
Okay, cool. Is it possible for cycles that aren't disjoint to commute? Is the identity disjoint from everything, or is it disjoint from nothing?
I don't know.
Okay, maybe we're getting off track.
Well, so like another thing I was thinking of is, like, I guess this is coming up in the inverses, but I feel like the inverse of things have to involve the same numbers.
Oh, yeah, I think so.
But inverses always commute with the
Yeah,
thing
good
it's
point.
inverting.
Good
so,
point.
all right. It seems like commuting is a complicated subject.
Okay.
All right. Let's just try part 6, since we remember part 5 from the first worksheet,
Mm-hmm.
and we were very solid on that.
What?
Maybe.
Part 6, we remember part 5 from the
sorry,
first worksheet. What first worksheet?
Well, the worksheet we did on the
In
first
class.
in class, yes, the last
The
worksheet
only one.
that we had in class. List all elements of S3 in cycle notation. We did that.
Oh, yeah.
And then we also found the order of each.
Oh, yeah.
So I remember that being fine at the time. I don't remember it now, but I'll look back at it after class.
Oh, yeah. That's 5.
Okay. Oh, great. We're in part 6 up anyway. Great. So.
Okay, so we want to find the inverse of 1, 2, 3, which means, so what does 1, 2, 3 mean? It means that 1 goes to 2, 2 goes to 3, and 3 goes to 1.
Yeah.
So we want something that sends things the opposite direction. So we want 2 to go to 1, and 3 to go to 2, and 1 to go to 3. Because we want, when we multiply them together, we want to get back to where we started.
Yeah. Okay, so can you say that one more time?
Maybe. So we
2
want
goes to
2
1.
go to 1, 3 to go to 2, and 1 to go to 3.
Okay. So 2 goes to 1, 3 goes to 2, so that would be like...
Maybe? Why don't we check?
Let's check. That seemed like it was too easy. Let's check.
Okay, so here we have 1 goes to 2, and then here we have 2 goes to 1. So 1 goes to 1. How do I denote that? Like 1 didn't do anything.
Just close that parenthesis.
Okay.
Okay, great.
Okay, so then 2, what does 2 do?
2 goes to 3.
Mm-hmm.
3 goes to 2.
Mm-hmm.
Okay. So close parenthesis. Okay.
Sure.
So far, so good.
This is weird. Why did we never do this before?
Well,
Like here we had a 7,
yeah.
but we didn't ever do anything.
I mean, I
with
guess we
7.
could have just added a 7, right?
Okay.
Which just says 7 goes to 7. Because that's what we were thinking, is that 7 doesn't show up, and so 7 goes to 7.
Okay.
And this is just saying 1 goes to 1, 2 goes to 2.
Okay. Yeah.
Okay.
Good point. We should have done that probably. Okay.
Yeah, probably.
Actually, we should ask our instructor, which is us.
All right.
Okay. Anyway, so this means that 3 has to go to 3 here, right?
Well, it should.
3 goes to 1 and 1 goes to 3.
Yeah.
Okay.
Yeah.
So instructor meta comment is that we would usually write this as just 1
Mm-hmm.
to say that everything goes to itself. I mean, in principle, so in general, we don't write these 1 cycles. However, if we wanted to write this without 1 cycles, we would write nothing.
Right.
And it's hard to indicate that you're talking about an element if you write nothing. So we use 1 in parentheses as the convention to indicate the do nothing action or the identity.
Yes.
Okay, so that's meta commentary.
Okay.
Great, let's move on.
So this was super easy with the 3 cycle, but I don't really understand what happened.
Okay.
So it just sort of accidentally was easy. So let's...
Okay. Okay, so we want to find the inverse of 1, 2, 3, 4.
Yes. So last time we started this by doing 2 goes to 1. So I wrote 2, 1. Does that seem like a... Do we want to start that way again?
Oh, by the way, should we have checked the other direction of multiplication?
Oh, probably. I mean, technically, yes. You should check that things have inverses, but I think there's like a theorem in the book that inverses are unique. I think it's theorem 7.2.
Inverses are unique, but don't we have to be able to multiply on the left or the right?
That's a good point. That's a good point.
So if I do this in the opposite order, the hope would be that I would still get this.
Do you just want to do that?
Yeah, let's check
Let's
this
just
real
do it.
quickly.
Great.
Okay, so I'll go 1, 2, 3, 2, 1, 3. Okay, so here, so this is the opposite order. Again, I'm going right to left. So here 1 goes to 3, and then here 3 goes to 1, so 1 goes to 1.
Yeah.
And then 2 goes to 1,
Mm-hmm.
and 1 goes to 2, so 2 goes to 2.
Yeah.
And finally 3 goes to 2, and 2 goes to 3.
Okay.
Okay, so it's the same thing. It's also the identity. So this was in fact, this
Mm-hmm.
was in fact the inverse.
Yeah, let me write that down. So I guess what the notation would be.
By the way, we noticed earlier that we could sort of cycle the order that we wrote these.
Yeah.
So I think that this is also the same as 1, 3, 2.
Yeah.
So these two elements are the same. Either one of them can be seen as the inverse of 1, 2, 3 inverse.
Yeah.
Okay, cool. Okay, so now we're trying to find the inverse of 1, 2, 3, 4.
Yes. Right. So we want, let's see. So in this case, we want 4 to go to 3, 3 to go to 2, 2 to go to 1, and 1 to go to 4.
Right. So in other words, we want to sort of like, a cycle is written where we move that direction, and sometimes we move clockwise. When we want to look for the inverse, we're sort of moving counterclockwise. We're cycling the other we're cycling that way rather than that way.
Can I just write it backwards?
Maybe. Okay, why don't we try?
Okay, let's try. Okay.
Okay, so here 1 goes to 2, and here 2 goes to 1.
Okay.
So we have 1, then 2.
2 goes to 3. 3 goes to 2. Okay. 3 goes to 4. 4 goes to 3.
Great. And then 4 can only go to 4.
Yeah.
Okay, so this is also the identity. And I guess we should check it the other way
Sure.
also.
Yeah, just to be safe. 1, 2, 3, 4.
Okay, so 1 goes to 4, and 4 goes to 1. 2 goes to 1.
1 goes to 2.
Yeah.
3 goes to 2. 2 goes to 3. 4 goes to 3. 3 goes to 4.
Yeah.
Okay.
Cool. Okay, so that's the identity. So in fact, writing it backwards gives us the inverse.
Yeah,
That's nice.
it is
It's
nice.
an easy way to write the inverse.
Cool.
Okay, and then we have one more that we have to find the inverse of 1, 2, 3, 4, 5.
Uh-huh.
Okay, so based on what I know about matrices, usually I expect the inverse of the inverse to be what I started with.
Yeah.
So maybe that's a good conjecture.
Yeah. Can I erase this?
Yeah,
Okay.
definitely.
Yeah, we're good here.
Yeah, so I conjecture that the inverse of the inverse is 1, 2, 3, 4, 5.
Mm-hmm.
And so why don't we just try that rather than trying to figure out what it should be?
Yeah.
Because
So I don't think this is going to be special to these things.
no, I agree.
Do we want to just try to do it for a group?
that to show that the inverse of an inverse is the element itself?
Yeah.
Why don't we try this one first?
Okay, let's do this one first.
And then we can try to show that
All right.
if once we believe it.
Okay.
Okay, so we conjecture that 1, 2, 3, 4, 5 inverse is equal to 1, 2, 3, 4, 5.
Yes.
So this is conjecture.
Yep.
Okay, and to check that something's the inverse, we just multiply it by
Right.
the thing. So the thing is 1, 2, 3, 4, 5, and we multiply it by 1, 2, 3, 4, 5. Or sorry, the thing is 1, 2, 3, 4, 5 inverse. And we multiply it by 1, 2, 3, 4, 5. Oh, well, I know how this is going to turn out. 1, 2, 3, 4, 5 inverse times 1, 2, 3, 4, 5 must be the identity. That's the definition of inverse.
Right.
And the other way also holds, because that's the definition of inverse. You're right. We could have just proved this for groups.
No.
No?
No, I think so, but I'm a little bit confused because I guess, like, what does this notation mean?
It means the inverse.
The inverse. So it's just a thing that when you multiply by this, you get 1.
Mm-hmm.
Okay.
So, I mean, I think that what you said earlier about doing this in general for groups is right. We don't have to know what an inverse is to know that it's the inverse.
Oh, like you don't have to have it written as a cycle to know that it's the inverse of this thing.
Right.
Oh, yeah. That's a good point.
So if we wanted to do this for groups, or maybe I should have said let G be a group. And I want G to be an element of the group.
Yes.
Our conjecture is that G inverse equals G.
Yes. I'm just going to move our recorder down a little bit here.
Okay.
Get some more space.
And I think that we just prove this the same way.
Yeah, I think we just multiply by G, right?
Yeah, I mean, this is what it means to be an inverse. Oops. Oh, okay. So we know.
It's a lot of negative ones going on right
I know.
Okay, so.
Well, I'm writing what I know about G inverse.
Okay.
I know that G inverse times G inverse should be the identity.
Okay, I'm with you now.
But we also know that G inverse should be the identity.
Yes.
And we know that inverses are unique.
We do.
I guess we used that there. Did we? I think we used that there.
Yeah, pretty much.
Secretly. And I think we have to check the other direction, but we're out of space, and we also know that if something's an inverse, it's an inverse on both sides.
Okay. Yeah. I think that whenever we are working on our own separately later, I'm going to figure out what this is in cycle notation, like before, and actually multiply these. Because here, somehow we didn't really, like multiplying these didn't feel the same. There's no work that we were doing. And I kind of want to see it happen. But,
yeah, maybe unsatisfying.
But you're...
Oh, but we know how to do it. You just write it backwards, right?
We just write it backwards. So I think on my own later I'm just going to do that.
Okay,
because you had a very nice abstract version, but I'm a little... I want to watch it happen. So.
Okay, cool.
Yeah, okay. Well, thanks, Becca, for your insights.
Yeah.
It was great working with you today.
Yeah, great.
Yeah.